Hi, I want to show you a little bit more about the Riemann sum, and this time we'll kind of get into the nuts and bolts of the math and the summation and what all of that means. So we'll go ahead and take a look at let's take a look at a simple function here. How about this one? Y equals, well, try that one more time. F of x equals x squared. Okay, and what we're interested in finding is basically this: the area from 0 to 3 of x squared dx. So the integral from 0 to 3 of x squared dx. If we graph it, it looks like this. Okay, and let's make that, we'll call that 3, we'll call that 0. So we're looking at this area right in here. Okay, so the Riemann sum, remember, very powerful. We're going to take out our samurai sword of calculus and we're going to cut this up into little pieces like this. And remember how we label them. We label them x0, x1, x2, all the way out to xn. Okay, now it looks like I've cut this up into 1, 2, 3, 4, 5, 6 pieces, but realize that I could really cut this up into as many pieces as you want. That's why I called this one xn. It's going to help us in our analysis in a little bit. Okay? So now we got to figure out some of our notation. Remember, we need to figure out the area of each of these rectangles, and we approximate that by finding the height times the width. So let's do this. Let's take a look at the width first. We call that delta x, okay, from our notation from last week. Delta x is just the width of the interval, b minus a, over the number of intervals. The width of our interval is 3, so our delta x is just 3 divided by n. Okay? The other thing we need to do is to figure out what the height of our rectangle is. And now we have to decide, do we want to use left-hand endpoints or right-hand endpoints? So in other words, do we use this right here as the height of our rectangle, or do we use this one as the height of our rectangle? Okay, let's go ahead and use right-hand endpoints. And I just picked that just because I felt like it. But it'll work either way. If you're using right-hand endpoints, the area of the ith rectangle is equal to, okay, now let's take a look. This is the first, the second, the third, the fourth. The right side is x1, x2, x3, x4. So it looks like the ith rectangle depends on the ith x value. Does that make sense? If we're looking at the second rectangle, so the first, the second rectangle right here, we're going to find our height by looking at the function value at x of 2. So that's going to be our height times our width. And if we did the left-hand rule, this would be x of I minus 1 instead. So there we go. There's the area of our ith rectangle. All we're going to do is add up all of our rectangle areas. I equals 1 to n, like that. Okay, now let's go ahead and substitute in what we know. This is equal to the sum I equals 1 to n. Now f of xi is equal to what? Okay, now we got to think about this for a sec. Xi is how many intervals over, right? Well, what's the size of each interval? 3 over n. So I'm going to just put this over here on the side. Xi is equal to the starting place, 0, plus the number of subintervals times each of the subintervals' width. This tells me where xi is. So x1 is 0 plus 1 times 3 over n. The third one this is the fourth one that I've shaded in, is 0 plus 4 times the interval width, 4 times 3 over n. That makes sense. There's 1 interval width, 2 interval widths, 3, 4. There's x of 4. So this is going to end up being f of I times 3 over n times delta x. Now we can do some more substitutions. I is 1 to n. Now f of stuff is just stuff squared. So this is going to be I times 3 over n squared. Delta x is equal to 3 over n. This is equal to I equals 1 to n of I squared 9 over n squared times 3 over n equals, and I'm just going to do a bunch of algebra here, 27 I squared over n cubed. Okay? Okay, now what we talked about last week is that any constant we can take out and put it out in front of the summation. So I'm going to do that with the 1 over n cubed. 1 over n cubed, sum I equals 1 to n of, I should do that with 27 too, shouldn't I? I squared. Cool. And then we can simplify this summation using the formulas that I showed you the other day. The sum of I squared is just going to equal n times n plus 1 times 2n plus 1 all over 6. Okay, and that's a formula. You probably should know that. I guess in the scheme of things it's not terribly important, but if you can remember it, fine. Okay, now if I multiply all this out, 27 over n cubed, and put that 6 out in front, I get n times 2n squared plus 3n plus 1, which is equal to 27 over 6n cubed times 2n cubed plus 3n squared plus n. Okay, now look what happens. If I simplify this, I get 54 over 6, and every other term is going to be something over something with an n or an n squared or an n cubed in, or n squared or an n cubed. Not just n or n squared. Basically, there's going to be an n down here. Okay, what I'm going to end up doing with this Riemann sum then is taking the limit as n goes to infinity. If I take the limit as n goes to infinity, the only term that's going to be left is that one, because these with the n in the denominator are all going to go to 0. And so the area underneath that curve is 54/6, and I guess that equals to 9 if you simplify it. That's how you do a Riemann sum. Basic idea, chop it up in little pieces, figure out which side of the endpoint you want to use for the height, figure out the area of the rectangle by looking at the function value times the width, adding them all up, and then taking the limit as n goes to infinity, as the number of subintervals gets bigger and bigger and bigger. And what will happen is you'll always have terms with an n in the bottom. They'll all go away. You'll always have one or two terms that always stay because they end up where the n's cancel. And that's what's cool about Riemann sums.